This page is important is because it describes where the shapes come from. We've already been talking about hybridization, and we've been talking about how these atoms, when they bond to the central atom and then they kind of bond outwards from it, they end up with these specific, consistent geometries or structures. You can just think of it, it's how the atom looks. Up here, we were talking about these kind of funny combinations that you end up with where you take your original SMP and then they combine together. So you'll notice in this case, right over here, this one gave us two of these little combinations. And there's like, each of them had half of a s orbital and half of a p orbital. So when you put both of those together, you get this kind of coming off the atom. What this is it's where the electrons are. Like if this is the middle atom, so I'm just gonna I'm gonna put Be in the middle. And then Be has a bond to fluorine and another bond to fluorine. And so what it is we've got those two electrons in there that are making, that bond that we usually call a line. But remember, they aren't just sitting on the line. That's just how we represent it because it gets more and more complicated the larger the picture is. And so we just use lines to represent what they're doing. But they aren't actually staying on the line. We know they actually are hanging out in this space. It's like if you take a snapshot of the electrons moving really, really, really fast. But if you take that snapshot and you get them moving really, really fast in that area, then it's kind of like this is the overall shape that they end up taking the form of. And then again, there's a pair over here, and again, they move really, really, really fast, and so this is the area that those electrons are in. And the left is one of the SPs, and then the right is the other SP. But anyways, these hybridizations, this is the reason behind the shapes. And it's really fascinating because it doesn't really matter what that central atom is, as long as, like this one doesn't have any lone pairs in there, as long as it has a matching lack of lone pairs on the central atom. It has the same number of atoms on the outside that have the same number of electrons to contribute, then you still end up with the shape. So this shape will repeat itself in many, many, many different contexts of different combinations of atoms. All right, so I'm going to clear this off just a little bit. And so what we have are 5 different shapes that come up. And then you're going to find that we do this other naming, and it's called, this is electron geometry. This is the beginning of the shapes. And then we're also going to be talking about molecular geometry. So electron geometry is where it started, and then of course we had to revise portions of it to account for variances. But it's the same variance, like it's the same changes that happen for every shape. So again, it's a really great overall trend. These right here are the ones that will be seen most commonly in organic chemistry coming up. And these are more for like catalysts potentially in organic chemistry. Or if you get into industry, this grouping here to here are very, very important for industry and the shapes of things that are designed for industry. So what are these shapes? Why are they named what they're named? We have a lab coming up that will explain it better. But this one right here, trigonal planar in chemistry, when we use trigonal, we use it to kind of represent anytime we're talking about a triangle. And then we use plane to say that the thing is in the plane of the page. So, and if I'm going to draw it like 3-dimensionally, so if that's a page, what I'm saying is that the overall outer shape of the atom looks like a triangle. And so you can see right here, you can imagine there's your triangle. That's why we call it trigonal, triangle. And it's in a plane. It's not like coming out of the page and being all 3D. Then tetrahedral. This one is harder to see, but we have another picture that helps represent it a little bit better. But this is not flat. So 2 of these are sitting in the plane. This one's coming out at you, and like this one's going back behind your page. But we have some pictures that in a minute that'll help. But if you'll just bear with me, this one has some, if you take this section, it kind of has some triangle shapes to it. And then the base has a triangle shape to it. It has a total of 4 triangle faces. That's why we call it tetrahedral. It's like a different naming style was used for octahedral and tetrahedral. It has to do with the number of triangular faces that the object makes, the molecule makes. Again, I'll show another example of that. We also have trigonal pyramidal. So if you take this planar right here, this triangle, and if you make it perpendicular to the page so that it's like a plane in the page, so there's our triangle right there. And then if you also put an atom going up and down, that's trigonal bipyramidal. And the reason that it says trigonal is because the base is a triangle, and then this kind of makes a pyramid in each direction. Bipyramid. And then again, like I said, this octahedral has more to do with the faces. And this kind has like a square shape here, and then there's like a vertical up and down atom that comes out of it. So these are the shapes. So let's go back and just practice matching these names with your worksheet. And here's the worksheet over here. This is chapter 4. If you go to the very end of chapter 4, you will see that we have already drawn several structures. All you have to do for these is look at the electron density. So you can see we have options of 2, 3, 4, 5, or 6. So electron density, that's either where there's a bond or where there's a lone pair. Either case, we're counting them as the same. This isn't exactly correct because we do kind of change it up a little bit when we're talking about lone pairs. But for the electron geometry, and we definitely do use electron geometry when we're naming things, we count the regions. So like in this right here, you can just tell that the only way to get between the hydrogens is if it's in a line. So that one is linear. I've gone ahead and written these shapes over here, but I'm going to show you how to match it up. So we're going to start at the second one. Anytime you just have two, it's going to have to be linear. So in this case, this beryllium has right there and right there 2 regions of electron density. They're bonds. Remember, in this naming, though, we also will count lone pairs. He doesn't have any, but we would count lone pairs. 1, 2, 3 regions of electron density. So this is when you have 3, we name it trigonal planar. If you have 2, it's linear. You can see that here. This one has 1, 2, 3, 4. So right here, 4 regions of density, tetrahedral. And you can see I've written tetrahedral over here. And you can rewind this or just pause it at the end to get the names. I'm just trying to kind of get the idea across of what you do. And you're going to have an opportunity to practice that too. So here's where we start including lone pairs in this naming. We have 1, 2, 3 bonds and a lone pair. So each circle, we still are at 4. So we write the word tetrahedral over here. Now this is going to change later, but we have to know this naming style also. So you would name tetrahedral for this one. And then here, 1, 2, 3, 4. Again, 4. So it's still named tetrahedral. Let's go on to the next page. So let me scooch it over. We have 1, 2, 3, 4, 5 regions. So that falls us here, and so that's trigonal bipyramidal. In this one, we still have 1, 2, 3, 4, 5 regions. Again, 5. Trigonal bipyramidal. 1, 2, 3, 4, 5. 5 trigonal bipyramidal. 1, 2, 3, 4, 5. Trigonal bipyramidal. 1, 2, 3, 4, 5, 6. Octahedral. 1, 2, 3, 4, 5, 6. Octahedral. And 1, 2, 3, 4, 5, 6. So we're just looking at that, a region of electron density. We're saying either the bonds or the lone pairs are equal regions of electron density. Now, you go ahead and fill out the next 2, and I'll show you what the answer should be. I want to be clear that this is per central atom. So we do have an element, a molecule in here that has more than one central atom, and it's here. So you would do it for each of them. So for example, the carbon would be 1, 2, 3, 4 regions. And then the oxygen would have 1, 2, 3, 4 regions. All of the rest of these just have one central atom or no central atom. You can see the no central atom. So go ahead and fill these out. The other thing you should note is that I know that this looks like 1, 2 regions, but it isn't. Those are all kind of considered in this naming system. For the shape of the molecule, it's considered one region. So this would be considered 1, 2, 3. Also, you'll notice that we don't count the outside electrons. We're only looking at the ones coming off of the central atom. So see what you come up with all of that information in mind.